Welcome back. We're going to continue learning about transformations of functions today. We're going to be going over graphs of square and cube root functions, graphs of exponential functions, and graphs of logarithmic functions. We talked previously about the different transformation rules as far as horizontal shifts, vertical shifts, um, horizontal or vertical stretches, and we also talked about reflections over the x and the y-axis. So this some of this is going to be review um, in terms of what we're covering with the horizontal and vertical transformations, but we're also going to be looking at how we can uh, use those transformation rules alongside of plugging in values for x in order to find out what the corresponding y values are. So let's take a look at this first example here. Actually, before we do, here's the reference guide for horizontal and vertical transformations. If you need to see that again, that's fine. Go ahead and take a screenshot of that if that's helpful for you. This was on our last lesson on scaling functions vertically and horizontally as well. Let's look at example one. So example one gives us a parent function, and the parent function is y equals the cube root of x. And it shows us the graph down below here. And for this, we want to figure out what's the new graph going to look like of the negative cube root of x minus 6. So a couple of things are happening here. The first thing that I notice is this minus 6. That's going to shift everything down 6 units. Now, the graph is also being reflected over the x-axis. So we can see that because there is a negative in front of the function itself. So it's not just making the x negative, it's saying the negative of the function. So this is a reflection over the x-axis or a vertical transformation. So let's take a look at what this reflection is going to look like if I just put the points from their original to where they are going to be reflected to. So here's our original points. A reflection would reflect it over the x-axis and land there and there. Now, if we move those blue points down 6 units, each of these are 2 units each. So we're going to go 2, 4, 6. And our blue point here would end up here. And our blue point here would end up 2, 4, 6 there. So our graph now, we're going to look for the corresponding graph that matches with that. So we've got the point 8, -8, and -8, -4. So I see that on graph A, 8, -8, and -8, -4. That looks like graph A to me. Notice how the graph is like in the opposite direction. So it was kind of like uh, an S, and now it's changed into a Z. So that's what the reflection is going to look like when it reflects over the y-axis for a cube root function. Okay, so that's example one. Looking at the next example, we're going to see some more transformations. If we look inside the square root, we have x minus 2. Now that follows the same rule of when we had something like x minus 2 in parentheses for some functions, where if there's a minus 2, we're actually going to go forward to the right 2. So here we're at 0, 0. If we're just looking at this part under the radical, that's going to move that point here to 2, 0. We also have a shift down 6, so we could move this point now down to here. And we have another transformation of multiplying this by 4. Just trying to zoom in, make sure we have enough room for all this. Okay, so we're going to multiply this by 4, and that's going to cause a stretch. Now, a couple things that we can do extra from the last example, we just were able to find out it was. But here's what we can do when we have a square root. When we have a square root, a nice number to plug in is to make the number that's underneath the radical equal to 0, because the square root of 0 is just 0. So in this specific case, we can plug in 2 for x, and that will give us 0 under the radical. So we have f of 0 is equal to 4 times the square root of, or excuse me, f of 2 equals 4 times the square root of 2 minus 2, plugging in 2 for x, not 0 for x, and then minus 6. So this is going to be 4 times square root of 0 minus 6, and this is 4 times 0 minus 6. And it looks like we have some of this cut off. It says which of the following, but I'll just make a copy of this and we'll see if we can graph it ourselves. So let me copy this here. Just copy this graph. And we'll see if we can get a good estimation of what it's going to look like on here. That got deleted somehow, but that's okay. All right. So continuing this, f of 2, we have 0 minus 6. That's just 0 minus 6 is negative 6. So we know the point 2, negative 6 is on our graph. So we'll plot that point, 2, negative 6. Okay. And we can start plotting some other points as well, and just to get a good estimation of where all this information would go. Well, let's see what happens now if we get a 1 underneath the radical. So if we have a 1 underneath the radical, we would have to plug in 3 for x. So we have f of 3 is equal to 4 times the square root of 3 minus 2 minus 6. And that's 4 times square root of 1 minus 6 gives us 4 times 1 minus 6, which is 4 minus 6, which equals negative 2. So this is 3, negative 2. So now we've got another point at 3, negative 2, which is right here. So now we sort of have a graph that's starting to look like something like this. Now, negative 6 means that it can't go below negative 6. So we've got an asymptote there at negative 6. It can't go any lower than that number. And the reason is, whatever we plug in here, we can't have a negative square root. So the smallest value that we can have inside this square root is a 0, which tells us our very smallest y value is going to be y equals 4 times 0, or 0 minus 6, which is y equals negative 6. That's our smallest y value that we can get. Doesn't matter if we plug in more negative numbers for this x value, we would then get a negative something this with like this, like a negative, we'll just say negative 7, square root of negative 7. You cannot do that. That becomes an imaginary number. I think we'd covered imaginary numbers in some earlier lessons, where whenever we have a negative square root, it becomes I. So we can only have positive values or 0. So that's how we have this asymptote down here. Let's go ahead and graph this on Desmos just so we can see the exact graph, just because that got cut off from earlier. So let me let me share my different screen here, and we'll go to Desmos and we'll take a look and see what that's going to look like on the graph. So our equation was y equals 4 times the square root of x minus 2. Then we're going to press over on the arrow key, and then we press minus 6. We're going to zoom out a little bit. Take a look here. So yeah, we can see that there's no values below negative 6, and that kind of matches what our graph looked like on the sketch of the graph. So it's stretched vertically more so than the original. In fact, let me graph the original parent function. So here's the original parent function, y equals square root of x in blue. And that's our transformation. That's what's happened. So it's gotten shifted down 6 and then stretched vertically so it looks taller. That's our new red graph there. Okay. All right, let's go to the next example. And hopefully those multiple choice didn't get cut off on the next one. Looks like they didn't. So here's our next example. We have a same parent function. Actually, yeah, same parent function as number 1 with a cubed root of x, for example, 3. So now it's saying, let's find this graph. So we've got to figure out what is the transformation that's happening on this graph. So the first thing I'm noticing is we have a +6 underneath the square or underneath the root. And so that means that everything's going to be shifted left 6. It's the opposite sign when it's underneath the radical. So left 6, everything's being scooted to the left 6. And um, we're also going to scale this by a factor of 3 is that's how we say this. And these are a little bit tougher to graph on Desmos because we don't have a cube root option. If you know how to do cube roots with exponents, that's great. You can give it a try. But I think that it's good to just look at these and try to figure these out this way instead. So we're going to say everything's moving to the left 6 and being scaled by being multiplied by 3. So we're going to use our same or a similar technique. We want to see what would happen if we find the cube root of 0. If we have the cube root of 0, that's just 0. So what can we plug in for x to make it 0? Well, -6 plus 6 is 0. So we'll find what is f of -6. And that equals 3 times the cube root of -6 plus 6, which equals 3 times the cube root of 0, which is 3 times 0, which just equals 0. So this is -6, 0. That's going to be on our new graph. So we'll take a look here and we'll see where is -6, 0 on our new graph. I see one at B and at D. Now we can automatically cross off A and C. Okay, let's see now what would happen if we get the cube root of 1. So if we get the cube root of 1, then that's also just going to be 1. So we'll plug in to get 1, f of -5. And this is 3 times the cube root of -5 plus 6. That's 3 times the cube root of 1. And that equals 3 times 1, which is equal to 3. Okay, so now we've got -5, 3 on our graph. And that's a little bit tougher to see on here, I think, because 3 is an odd number and these are going up by 2s, but that's okay. So we've got -5, 3. Looks like that's it on B. And let's zoom in a little bit more here. And on D, it looks like the 5, it looks like we're at -5, 2 for D. So we can cross out D. So the entire point of doing this is to figure out what are the transformations that are occurring so that we can get a basic idea of what the graph looks like, and then we plug in some points that make sense to plug in, which helps us to finalize which graph that it would be. So again, for B and D, we're moving left 6 units, and that's where our x-intercept is at -6, 0. And so then we're going to find, well, what can we make this so we have a cube root of 1? Another thing that you could do if you wanted to check one more point is if you know some cube roots by memorization, we could say, well, the cube root of 8 is 2. So then we can figure out, well, f of 2, that would give us 2 plus 6 under that cube root. And so we'd have 3 times the cube root of 2 plus 6. And that's 3 times the cube root of 8. And that's 3 times 2, which is 6. So 2 comma 6 would be on our graph as well. And now we can start to see for sure Where is 2, 6 on here? If you weren't quite sure about our point from earlier that we found, which was negative 5, 3, you could find where is 2, 6. So 2, 6 looks like that's on graph B also. And we get 2, 4 on D, so that's not correct. All right. So let's take a look next at exponential functions. We're going to use a similar method with exponential functions with plugging in some values, but let's think about what those values are that we want them to be. So first we have uh, this function that's y equals 1/2 to the power of x. So we have that function there, and it wants us to graph this function y equals negative 3 times 1/2 to the x plus 5. Now, we have our main function here, and we have plus 5. That's the first thing that I would look at. That means everything's going to be shifted up 5. We also have the entire function being multiplied by negative 1, or negative, in this case, negative 3. That's going to cause the graph to reflect where the x-axis. And if we plus 5 from that, and I'm just doing a very rough sketch, it's going to look something like that. And I really shouldn't have shifted it over. Should have overlapped it a little better. So that's just kind of a rough sketch of what the graph should look like as that red line. Now let's finalize our sketch so we can start crossing some stuff out here. And this was my work from earlier. I meant to erase that. So now we can cross some stuff out. So we can cross out A and B. And we have C and D now to choose from. So when we're looking at exponents, a good rule to remember is anything to the power of 0 equals 1. 7 to the 0 equals 1. 1,000 to the 0 equals 1. A to the 0 equals 1. 1/2 to the 0 equals 1. So if we plug in f of 0, now we have f of 0 is equal to negative 3 times 1/2 to the 0 plus 5. And that's negative 3 times 1 plus 5, which is negative 3 plus 5, which gives us 2. Put it equals there. That equals 2. So we know the point 0, 2 is on our graph. And that's going to be our y-intercept, 0, 2. And we've got that on graph C. And that's the only graph that has 0, 2. Another number that's really easy to plug in for x is as long as there's just x there and it's not like x plus something else, we want the exponent to equal 1. That's another way that we can solve these. Okay, some of this stuff got moved around here. We're going to do an interactive graph next. So we'll take a look at an interactive graph for our next example. Just means what can these values approach but never actually get to? And to explain that a little bit better, uh, we've got to figure out no matter what we plug in for x, what's the lowest or highest y value that we can get to. So no matter what we plug in for this x here, this number, 1/2 to the power of whatever that is, it's going to approach 0. Or it's going to approach a very large number, but 0 is as negative as it can get. We can think of it like that. And we might do another lesson on why that is, but I don't want to go too into detail about why that is right now. But if we plug in a number for any number for this and we bring a fraction to the power of any number, we're not going to get a number less than 0. So we'll just say 0 is our absolute lowest value that we could get. So let's pretend that this is all 0. 5 times 0 gives us 0, and we have negative 2, and that is our asymptote. We sometimes also see that as, uh-oh, I don't know what happened there. I think maybe I have to refresh this page here. Hopefully it gives us the same problem when we do that. Okay, good, it does. So we're going to bring the asymptote to -2. And you might see that as y equals k in the form y equals mx plus b. This is this would be b. Sometimes we call this k. All right, that's a little bit off topic, but the next thing we're going to do is we're going to plug in 0 for x to find the y-intercept. So I'm going to switch screens here, and I'm actually just going to copy this problem, and we'll put it on the whiteboard, and we'll see what that is going to equal. And we plug in 0 for x. So this is, okay. All right, so we're going to plug in 0 for x and see what we get. So this is f of 0 equals 5 times 1/2 to the -0 minus 1 minus 2. And I think this is a great example because we get a negative exponent here. And when we have a negative to the -1, it's the reciprocal of. So this becomes 5 times 2. Sometimes students think a negative means it makes this negative. It does not. It flips the fraction. So this is 2 over 1 now, or just 2. And then we minus 2, and this gives us 10 minus 2, and that equals 8. So we know now the point 0.08 is on our graph. I'm going to put that on our graph for now, and then I'll show you the final graph at the end. So I just put 0.8 on the graph there as one of our points. Um, Now the next thing I would do is figure out what can we plug in for x to give us a exponent of 0, to give us an exponent of 0. So we need to figure out what, or negative what, minus 1 equals 0. Well, 1 minus 1 equals 0, but that would actually be negative times -1, which would give us that +1 to make 0. So this is the part where you have to decide what you're going to plug in to make the exponent 0. And that takes a little bit of thought, I think. So we're going to plug in -1 next. So f of -1 is equal to 5 times 1/2. And now we're plugging in -1. So this is -1 minus 1. A lot of negatives there. And we're going to minus 2. So we get 5 times 1/2. And now this is +1 minus 1, which gives us 0. And so anything to the 0 is 1. And we get 5 times 1 minus 2. That's 5 minus 2. And that equals 3. So the point -1, 3 is on our graph as well. So we'll put that on our graph also. So we should have 0.8 and -3, 1 on our graph. And let me double check that I did everything correct. Or -1, 3, excuse me. -1, 3. That's messed up my graph there. Okay. So here's what the final graph should look like. So that's the final graph of 0.8 and -1, 3. Okay. All right. So let's continue. The next one is asking us for the transformation of, we have this graph here, y equals 1/3 to the x, and it's asking us for the transformation of 2 times 1/3 to the power of x plus 1 minus 7. Okay, so for this next one, um, this has, let me see here. This exponent is telling us that we're shifting the graph left by 1 unit. So all of this is going to move to the left just 1 unit over. So that would look something maybe like that. We're also going to shift down 7 units. So now that's actually when I did the left, it maybe should just been like that. And then we're going to go down 7 units. So it's going to probably look something like that. And it's going to be stretched by a factor of 2. So it's going to be stretched out a little bit. Not much of a difference, not much of an incredible difference with that stretch, but it is going to be some kind of difference. So far, it looks like we're looking at either B or D for these. There's no reflection across the y-axis, so we can cross out A and we can cross out C. So there's no reflection there. That helps us get rid of some answer choices again. But we're gonna use the same method that we did before. We're gonna figure out what's the y-intercept. The y-intercept is when x equals 0. So we're gonna do f of 0, plug in 0 for x. So we get 2 times 1/3 to the 0 plus 1 minus 7. And so that's 2 times 1/3 to the 1, which is just 1/3, minus 7. 2/3 minus 7. That's going to give us a little bit less than, uh, excuse me, a little bit more than -7. So that's going to be 6, -6 and 1/3. So that's kind of a strange point to find on the graph, but you can estimate that point. So 0, -6 and 1/3. Let's see here. Looks like B and D have the same y-intercept at 0, -6 and 1/3. So I would say maybe before you find the y-intercept, just check what those are on the multiple choice. And once you check what those are, you can see if they match or not. If they do match, maybe just skip the y-intercept. Unless you want to start with just the y-intercept, you can do that too. If you want to just begin with the y-intercept before even considering the transformations, that might be a good first step also. But I'll leave that up to you. Okay, so we found the y-intercept. That didn't really help us narrow down any more answer choices though. Let's see what happens if we plug in, let's see here. We could plug in another number. Um, we could try to set the exponent equal to 0. So if we set the exponent equal to 0, we can plug in -1 for x. So f of -1 is equal to 2 times 1/3 to the -1 plus 1 minus 7. And that's 2 times 1/3 to the 0 minus 7. That gives us 2 times 1 minus 7. And that's 2 minus 7. And that gives us -5. So the point -1, -5 should be on the graph. So let's see if we can find that on here. So -1, -5. That looks more like that. Those both also might be on the graph. Let's see here. So -1, -5. That would be about here. And this is -1, -5. So those both look like they're on the graph also. Okay, so let's change our strategy a bit here. So we tried making the exponent equal to 1. We tried making it equal, or excuse me, we plugged in 0 for x, which made the exponent equal 1. We also tried making the exponent equal to 0, and we were still not able to narrow down B or D. So the next thing I would do is let's take a look at the graphs themselves, see if we can find a point that we can identify for certain on the graph. I see on either of them. I see a point that we know for sure on B. On B, we can say that's -4, 2. When we plug in -4 for x, we get 2 for y. So let's try that next. So f of -4 is equal to 2 times 1/3 to the -4 plus 1 minus 7. And if we also, just kind of a side note here, I forgot to mention the horizontal asymptote. -7 is our asymptote. That shows on all of our graphs here, though, but that means that it's approaching -7, and it never touches -7. But that's there on all those graphs. Okay, back to this. So -4, we're plugging in for x. So we plug in -4, we get 2 times 1/3 to the -3 minus 7. Now we've got to use our calculator for this. I'm going to use a calculator that's not on the screen, so I like this calculator better. But when you're calculating this, make sure you put the 1/3 in parentheses and then say to the power of -3. And it gives us a nice whole number, 27. 2 times 27 minus 7. And let's see, so we get 2 times 27 minus 7 gives us 47. Now 47 is not on the graph. We can't even see 47. This says the point -4, 47 is on our graph. For B, if it was B, um, it would not be correct. It's got to be answer choice D, because we get 47 when we plug in -4. So for answer choice B, we just got 2 when we plug in -4, and that's not right. So it's got to be D for this one. Okay, let's take a look at the next one here. And the next topic is logarithmic functions. We're going to use a similar strategy for logarithmic functions. There's a couple of rules that I think would be good to review for logs, though. If we have log base 10, we don't write the 10 on the base. We just write log. And our calculator can find what the log is of a log. If we have the log and then an index, that's our index inside the parentheses there. So our calculator will actually give us a value for these. So you can type in log 5 and you should get about 0.69897. That's if it's log base 10. And we don't always write the 10 there. In fact, usually we don't write the 10. So that's one thing about logs and how you can find that on your calculator. The next thing is log base. If we did log base 3 of 5, you can't really find that on your calculator. But you can find log base 3 of 3. The rule is that it equals 1. So same base, same index equals 1. That's one of our rules. I'm going to write it in terms of algebra and just write it like this. Log base A of A is equal to 1. That's one of our rules we need to know for when we're choosing what numbers to plug in for x. Another rule we need to know is that log 0 of any base, I'm just going to put log 0, is undefined. If you put that in your calculator, you will get an error. And if you remember from our last lessons on logarithms, that's because of, well, we talked about the snail rule, but let's take a look at if we did log base 10 of 0 and we said that equaled a, and we'll see if we can solve for a. So we use the snail rule. We say this is the base, and then we make a the exponent, and then we wrap around saying that that equals the index. So that's how we rewrite this as an exponent. We say 10 to the a is equal to 0. No matter what we plug in for a, we will never get 0. That's because if we did 10 to the 0, we get 1. If we did 10 to the negative 1, we would get 1/10. If we did 10 to the negative 2, we'd get 1/100th. We would never get to 0 no matter what we plug in for that exponent for a. So that's why log 0 is undefined. Okay, so that's another rule that we need to know. And then the last rule is log of 1 is equal to 0. And let's take a look at why that is. If we had log base 10 of 1 is 0, if we rewrite that as an exponent with the snail rule, it becomes 10 to the 0 equals 1, and that's a true statement. If we had log base 4 of 1, that also equals 0, because if we did the snail rule and rewrote it as an exponent, we get 4 to the 0 equals 1, and that's a true statement. Okay, so we're going to use these three rules in order to answer our logarithmic graphing equations. So this first question says, we have log base 3 of x graphed for us here, and we want to figure out what this graph is going to look like of log base 3 x minus 2 minus 1. Okay, so we first want to find the asymptote, and the asymptote is where the graph is undefined at. So when we have our index equal to 0, it's undefined. So we need to ask ourselves, what can we plug in for x to make this index equal to 0? If we plug in 2 for x, that'll give us 0. So f of 2 is equal to log base 3 of 2 minus 2 minus 1. And that's going to give us an undefined answer. So now we have undefined minus 1. Well, we can't really do undefined minus 1. That just is undefined. So our asymptote, is undefined at x equals 2. So we're going to have a vertical asymptote at x equals 2. The only graph on here that shows us a vertical asymptote at x equals 2 is graph B. That's the only one on here that will do that. So that's how we can answer this one very quickly, is just find the asymptote. That's the only one that has that asymptote, and we're good to go. Let's look at another one that not necessarily we can find immediately just by the asymptote. So this is an interactive graph, and I put just the answer for this interactive graph on here so we could look at some of the features on here. So we want to find the asymptote. We want to figure out when we plug in 0 for the index, where that asymptote is. So we've got to think to ourselves, what do we have to make x equal to have an index of 0? So what minus 3 is 0? Well, 3 minus 3 is 0. But we actually have to plug in negative 3 for that. F of negative 3 is equal to 4 log base 3 negative 3 is what we're plugging in for x, minus 3. And that gives us 4 log base 3 of 0. And that's undefined. That's 4 times undefined, which we cannot do. That's just undefined. So at negative 3 is undefined, and that's how we have our asymptote right here. Okay, let's check out how we got the rest of these points, though. We've got a point at negative 4, 0. So if we plug in negative 4 for x, let's see what we get. So we get f of negative 4 equals 4 log base 3 of negative 4 minus 3. So we get 4 log base 3. That's positive 4 minus 3. 4 minus 3 is just 1. Okay, we found out earlier log base 1 is 0. That's one of our rules here. So this is just 4 times 0, which is 0. So that's how we got this point. Okay, and we've got another point on the graph at negative 6, 4. Let's take a look at how we got that one here. So I put at log question mark because we don't know what that is. I should have wrote log a equals 1. So you might have figured this out already since we talked about it a little bit earlier. We want the base to match the index. So we want this index to equal, in this case, 3. So we've got to figure out what are we going to plug in for x to make this equal 3. Well, if we plug in negative 6, that's negative 6, which is positive 6. And then we're going to minus 3 from that. That's going to give us 3. So we've got to plug in f of negative 6. And if some of these are kind of tough for you to figure out, just focus on this. Do a little bit of guess and check. You can use your calculator if you need to. And it might seem like I'm doing these really fast. If it does, don't worry about doing these incredibly quickly. We just need to figure out how can we make the index match, or the index match the base. So we're plugging in negative 6 for x, so we get 4 log base 3 of negative 6 minus 3. And that's 4 log base 3, 6 minus 3, 4 log base 3 of 3. Anything with the same index and base equals 1. So we get 4 times 1, and that equals 4. So that tells us negative 6, 4 is going to be on our graph. All right, we're going to look at one more here. This one says log base 2 of x is here. Now we've got negative log base 2 of x plus 4. This one's kind of neat because we can use our transformations rules. So the negative log, what's going to happen is this is going to make it, let me see here, the negative log, well, first of all, we're going to make it shift to the left 4 units. So that's the first thing we can think about, shifting left 4 units. But it's that negative is also going to cause a reflection over the x-axis. So it's going to be flipped over. So we can think of it like kind of like that. And then it's going to be shifted over 4 units. So let's take a look at what that one might be. If we shift it, if we flip it over, that's going to get rid of C and D. And then what we're going to do is we're going to plug in, we want 0 for our index. If we plug in negative 4 for that, that's going to be f of negative 4 is equal to negative log 2 of 0. And log 0 is undefined. So at negative 4, we should have an asymptote. And we can clearly see that at B. And we're just going to call it good for that one because there is no asymptote That is not an asymptote. You can see it's crossing -4 for A. So you can cross that one out. All right, so that's everything on transformations of uh, square root, cube root, exponential, and logarithmic functions.